Good afternoon, ladies and gentlemen. Thanks for coming. My name is Marcin and I'm a site reliability engineer from Google Ireland, based in Dublin. Um, I will be talking about engineering reliability, which is exactly what I do on a day-to-day basis. And just a few words about myself. I'm educated in sociology, statistics, and software engineering. I've been 5.5 years with Google. I started as a customer service person, and then I moved to be an internal developer for internal tools, and eventually a site reliability engineer. Before we start the actual tech talk, how many of you are engineers? Student engineers. Majority, wow. So I think you'll enjoy this one, because I'm going to talk about how to make systems big and how to make big systems perform. Google is obviously a big system itself, but it was founded in 1998 by just two PhD students from Stanford University in California, Larry Page and Sergey Brin. And when they started, they had 4 computers, which is cute by today's standards. It's currently headquartered in Mountain View, California, and we have offices in 40 countries. This slide says we have 33,000 permanent employees, which is a mistake, because now we took over Motorola, we have more than 55,000 people. That's an old slide. We spoke about Google's mission. I think someone had it memorized. To be honest, I don't have it memorized, but since I have it in front of me, Google's mission is to organize the world's information and make it universally accessible and useful. And obviously that started with a search engine, but Google sees many things as information. So for example, email is information according to Google, and hence we have Gmail. And music is information according to Google, and we have Google Music, which only works in the US as of yet. And books and academic articles are information, so we have Google Books and Google Scholar. And we have many more products. But every single of those products is guided by the principle that we have information, and this information has to be organized. So Blogger is a way of organizing human thoughts and human experience. Calendar is a way of organizing your day, and so on and so forth. Now, those products run because there are thousands of computers, but there are also hundreds of people who tend to those computers. And obviously there are people who program the products. We call them internally SWEs, which stands for software engineers. Those are people that develop your Gmail, your Googles, your calendar. We also have people who work physically with computers. So in each data center, we have people that we call hardware operations, which physically fix computers, which deploy fibers. They tend day to day to those computers. Somewhere in between, however, between people who write programs and people who deal with computers, we have people who make sure that the program that was written by some people runs on computers maintained by other people. And essentially that's a separate organization from software engineering and hardware operations, and we're tasked with maintaining Google reliability. This is a bit like a system administrator in your small company, but this is a system administrator that every 18 months needs to automate yourself or themselves out of the job, which means that tasks that I do now, in 18 months, I'm expected to have them fully automated. So it's a system administrator that is a damn good coder as well. Now, this job started in Google. So Google is credited with creating a site reliability engineering in IT, but currently many companies have similar positions. Amazon, eBay, Facebook, Spotify, They might call it a service reliability engineer instead, which I think is a better name, but it's exactly the same team. As I said, we're coders, so it's not a purely operational team, but we're also on call for our services. So for example, I'm currently holding a phone, and if something breaks and no one else can fix that, I'll have to leave you and fix that. But that means being on call. I'm in Tunisia, but you know, if duty calls, I'll have to do it. We also have our mission as site reliability engineers, and this is to serve every request reliably, quickly, and cheaply. And you have to pick all three. You can't sacrifice one against the other. The way we look at our work is we want to leave no query behind, which is the guiding principle behind site reliability engineering, and actually system administration as a whole. We try to serve every query, even if things are falling apart, right? Like hard drives are failing, power supplies are failing, people digging up fiber lines from our data centers, or trucks crashing into electrical substations, or birds going into our power lines. Things like that happen. If you run on a sufficiently big scale, you'll realize that things break. All things break in the worst possible moment. By query, we actually mean every request against our services, and we'll look at it, an example later. So I'm not only talking about the search query, a query will also be your Gmail, fetching your emails from the central server. Of course, leaving no query behind doesn't work in reality. The world is a harsh place, and we don't try to serve every query. We only serve 99.999% of them, because serving more would be dangerous or not feasible economically. But that's 5 nines, that's a lot. Okay, so what does reliability engineering mean? I'm going to spend the next 30 or 40 minutes explaining. But let's imagine that, as engineering students probably did, you wrote a web application, and it's running on your server, and it has a MySQL database behind it. How many people wrote an application like that? Who did it in PHP? Exactly. So it's probably your web server and your database server is exactly the same thing, right? It's running on one machine, and you can point your browser to it, and it just works. And that means you're done, doesn't it? That's the schema of your application. And yes, it essentially works. And you're done. Except, let's imagine that your small application becomes the next big thing in the Arab world, and suddenly 100 million people from all North Africa want to use it. Which I suppose is a great thing, but how do you cope with that? And that's where site reliability engineering comes into play. So what needs to change in your application so that you can serve 100 million users? Now, a quick note. The slides that you're going to see do not represent any particular Google system. They kind of represent the way we think about systems. As a matter of fact, more systems would be more chaotic than what I'm going to show you. There might be systems that are organized exactly like this, but it's not. I'm not talking about any particular system. So don't try to assume that it's like Gmail or maybe that's Google Docs. It might be, but not necessarily. First of all, let's figure out what 100 million users mean in practice. 100 million users, if they're active, and those are daily users, that could mean that each of those users accesses your application 10 times a day, which means 1 billion user accesses per day. And each user might cause 10 requests. So when you open a page, your CSS loads, your JavaScript loads, your Flash loads, a lot of things. Your Google Analytics is tracking this whole thing. So let's say that each user access causes 10 requests. which means an average throughout the day is 10,000 queries a second. But it's never really 10,000 queries a second, because that's an average. And an average, you know, if I put my left foot in a freezing water and I put my right foot in a boiling water, on average I'm fine. But it never works this way. So if you see graphs of big services within Google, you can see that Far East wakes up and our usage spikes. And then it's kind of day throughout Central Asia, and there's not many users there. But then Europe wakes up and things spike. And just before Europe goes to sleep, East Coast in the US wakes up, and it's another big spike. And then East Coast kind of goes to sleep, and there's West Coast, California. So it's never really 10,000 queries a second, but it's more like spikes of 20,000 queries a second and lows of 2,000 queries a second, maybe. Let's say that each query requires 10 disk seeks. Some would use more, some would use less. Disk seeks are actually the biggest bottleneck in the current serving infrastructure, but you always have bottlenecks. If we, for example, used flash disks, we would run into another bottleneck, which would be our TCP, the way that TCP protocol works. If we solved that, we would be, for example, limited by the processing power needed to process the I/O. It goes at such speed. So there's not an ideal world. There will always be bottlenecks. In this part, in our current situation, it's always disk. But let's say a disk does 106 per second. So we need to serve 200,000 seeks per second, which means that we need 2,000 disks. Now, back in the day, the philosophy was to put all of those disks into one big server and buy it from IBM or from any, big manufacturer that guaranteed it would stay up and perform very well, except when it didn't. So if that broke, your super expensive machine was not serving at all, and that was a kind of problem. So Google and other tech companies do something called warehouse scale computing, which comes from a simple realization that it's much more economical to use a lot of small servers, pretty much your home computers, rather than one big server. And if we have 2 disks per server, that gives us 1,000 servers. We normally store 40 servers per rack. Rack is a kind of a fridge that we put our our servers into. And at 40 servers per rack, we need 25 racks to serve this system. That's around 15 meters of square meters of space. This is obviously a very small service. It's not exactly as big as our data warehouses. But coming back to our cute little application, what needs to change if we're going to serve so much traffic? Well, you're going to need a lot of web servers, and we need to have a lot of databases. And they need to talk to each other. So if your one database is down, other web servers should probably talk to other database servers. So there needs to be some sort of connection. But for simplicity, let's assume that we're just going to call it web servers and database servers. Which might be a good idea for a very small and simple application, but once your application becomes more and more sophisticated, you actually start separating responsibilities between those servers. So you no longer only have web servers and database servers. You start to have many small sub-services within one service. And some of those sub-services might be shared between different services. So for example, you might have a web front end, and if you identify users, you might have an authorization front end, and user preferences. But those user preferences have to be stored somewhere, so you have preferences storage. And behind the web front end, you'd have a search front end, which then talks to the search backend, which talks to other subsystems. From those subsystems, do you think that any of those could be shared between different systems? Which one could be shared? Well, if you log into one of the Google services, you log to all of them, so probably authorization can be shared, right? Your user preferences could be shared. Probably we're going to use a synonym server here, so probably that could be shared between many, many services. So you no longer create a service from scratch. You start to reuse existing bits and pieces. But that's just a part of the story, right? Because once you have the system in place, you need to have a way of letting users get into the system. And how do you get traffic to 1,000 servers? Well, a simple way of doing that would be a DNS, right? But you can't just publish 10,000 IP addresses to the world. Your usual DNS will not be able to handle that sort of response. So you need a front-end load balancer to map a few IP addresses that we're going to send to the DNS response to a lot of backend servers. Typically, we'll either be using software or hardware load balancers. Hardware load balancers are faster, they're very expensive machines, but they're kind of dumb. Software load balancers are very easy to change, but they're not that efficient. So if you really want to combine flexibility with efficiency, you use a combination of hardware and software load balancers. So maybe on the network, in the network layer, you'd use a dumb hardware load balancer, but somewhere above that, in the application layer, you might use a software load balancer, which would be smarter. So in our little system, we have another element, which is a load balancer. And if you have many load balancers, chances are that you're going to have to load balance between load balancers, right? And usually the top load balancer would be a dumb hardware one. Lower down, you would have a smarter, less efficient one. But then, how do we get the traffic to our front-end load balancers? Well, obviously, I kind of answered my question already because we use DNS. We publish a few DNS addresses, but that also means that we need a DNS server, doesn't it? So in front of that load balancer, we put a network, but we also need to have a DNS server that would answer this query. Sure.
S'il vous plaît, ayez un peu de respect pour le speaker. Il s'est tapé des milliers de kilomètres pour venir ici. Alors, s'il y a des gens qui veulent sortir, qu'ils le fassent maintenant. Pour tout le reste, attendez que le monsieur ait fini. Ok? Est-ce qu'il y a d'autres personnes qui veulent partir? Toute personne qui veut partir, elle peut partir maintenant. Autrement, respectez s'il vous plaît la personne. C'est bon? Est-ce qu'il y a d'autres personnes? Merci beaucoup.
Okay, so once we get the traffic to the right place, and we know that our users are using the service, we also need to have a way of making sure that the servers are doing what they should be doing. So we need monitoring. We need to know how loaded they are. So do we need more servers? Or maybe we actually need fewer servers. Maybe we can repurpose our servers for another service that is seeing spikes. We need to know when they're getting overloaded, when we need more. We need to know how many requests they're handling, how many users we've got, so we can have predictions for the future, how many servers we need in the future. But most importantly, and that's the most difficult task, we need to find out if those servers are providing the functionality we expect. It's not whether they're up or down, how many requests they're serving, but how they are doing. And that's a very difficult part. We kind of do it by exposing parts of internal state of the server, and by looking at the internal state, we try to find out if the server is doing what it should be doing. But that's definitely the trickiest part. So we added monitoring here, and with monitoring that looks very much like Google services that I've seen. But that's a good day. Well, on a bad day, things will fail. And by the way, how do we monitor monitoring? That's another question. So the answer is we monitor monitoring. We put a monitoring over monitoring. But then what do we put over monitoring over monitoring? It's monitoring all the way down. But it's where do we stop? Where do we say, okay, we think we're done? That's also a very difficult question. How many layers do we need to make sure that monitoring of a monitoring of a monitoring is monitoring well? Sometimes it will not. Sometimes things will fail. And the law of dynamic negative says that anything that can go wrong will, and at the worst possible moment. Just to give you an example, the last couple of weeks, there was a hurricane in New York, Sandy hurricane, and we felt the impact of that. But when that happens, people are at home and they're Googling like crazy. But the same hurricane that makes them Google like crazy makes some of our data centers, flooded or inoperational. And obviously, we have trouble letting those people Google because data centers that would normally serve them are down. And that is an example of things that can go wrong at the worst possible moment because there's an event that causes the two things to correlate. But many things can fail, right? And at our scale, everything fails. Obviously, hard drives are failing, and then power supplies are failing, and then going to more serious stuff, switches, network switches will fail, and then power distribution units in a data center will fail, and then routers will fail that are driving traffic through the data center, and fibers will fail, and maybe people intentionally could dig up a bit of fiber and sell it somewhere. Power substations fail, and most importantly, software is not perfect. There are bugs, and things might go wrong in the software itself. But we need to plan for all those scenarios. Let's go through some of those scenarios. One of the failure domains that is least problematic for us is a machine. So to give you an example, a power supply unit fails after 100,000 hours on average. But if you have 1,000 machines, which we have for our service, that means one power supply unit will fail every 4 days, right? And you can easily see that because one machine suddenly goes offline, or it gets very slow because maybe just one core is broken, or it starts corrupting packets, or otherwise shows on monitoring that it's doing something strange. The action is simple. You just get traffic away from that machine, you ask people to repair it. But if the affected machine holds any data, you need to make sure that the data is available somewhere else. And most of the systems would be reviewed by people like me, site reliability engineers, to make sure that they would fail in a very nice way, that the data would not be uniquely available just on one machine, because as we know, machines will fail. That's a matter of design. Going to a more serious thing, switches fail. And if you see that those machines that are connected to one switch go offline at the same time, you know that it's your switch being affected. And again, the action is to get traffic away from affected machines and get someone to replace the switch. Again, if those machines hold data, you need to make sure that the data is available in other locations. If it's not, well, you kind of lost your data. By Google standards, losing data is the worst possible thing. And it happens very rarely because we have defense in depth, and the team that I'm working on is actually dealing with saving the most valuable data onto tapes and getting them from tapes if need be. So if a team thinks that they lost data, they come to us and we save the day, actually, hopefully. But again, this is a part of a review for a service, that it doesn't fail in a way that one switch brings down the entire service. The data has to be in multiple places. Another failure domain is a power distribution unit, and those are high voltage distribution units inside data centers. They operate at thousands of volts. If one breaks, then a large portion of a data center suddenly loses power, and that's a very, very bad thing, because many things are, many machines and many networking equipment pieces are actually required to be taken down very gracefully. They need to do a lot of things before they close. Same with machines. If things lose power very suddenly, they might not come back, and we see that a lot. If a data center goes down and it goes up again, we have a big loss of machines and equipment. And eventually data centers go down. Some failure modes can take out the entire data centers. For example, a hurricane like Sandy in New York, flooding, earthquakes. This happens very rarely, but it's definitely hardest to deal with, because the entire place is down. The bad news here is that some of our biggest markets are in some of the most unstable regions, because California gets its fair share of earthquakes, and New York and the East Coast gets its fair share of not volcano eruptions, hurricanes. Japan gets volcano eruptions, tsunamis, and earthquakes. So, for whatever reason, people choose to live in places that are pretty dangerous, and our data centers fail. But obviously, we need geographic diversity. So, if our little service is supposed to be really reliable, we need to host it in multiple copies in multiple places. So, we might host one in Dublin in a data center, might host one in Taiwan, might host one in Oregon in the US. But now, how do we make sure that the traffic goes to the right data center? That's a new problem, right? We don't want a user who is in Japan to go through Europe to be eventually served by an American data center, right? First of all, because it would be probably bad for capacity planning. But second, we probably want the user to get his answer very quickly. So we don't want to give him an extra latency for his query. So if we have multiple setups in multiple data centers, we need to do something which is called geographic load balancing. And commercial solutions exist from several vendors. I think we're our own. But it's not something completely unknown. And this is done by DNS. Essentially, a DNS response from Tunisia, for a user from Tunisia, would be a very different DNS response from user for a user in Japan. So if you ask, where is google.com from Tunisia, you would get one IP. If you ask from New Zealand, you'd get a very different IP. And that's the basis of our load balancing. Now, the other benefit of having multiple setups is that if one gets overloaded or one gets down, traffic might be redirected to another one. So, for example, if Australia fails, we might get served from Taiwan or Middle East or South America or Europe indeed.
Or Singapore.
Now, that kind of helps us to deal with failure, because when one of a big data center fails, we can take the traffic and serve it from another data center. And how do we do that? The same way we brought the traffic in, by changing the way DNS responds to queries. And obviously we need to figure out when to drive the traffic away, and we use monitoring for that. So we essentially use the same mechanisms for driving traffic into the data center and driving traffic out of data centers. Obviously, we should be prepared to serve requests at a redundant setup. So it's a traditional approach to reliability. If you think that one element will fail, just give it 2 copies, and the second copy will be just fine. It is indeed applicable to a lot of problems, and geographic diversity is also showing a redundant scheme. Probably we'll have 2 more data centers than we need, just in case one fails. But it's very expensive, and it's typically 2 times. We can't really afford to have 2 times redundancy. But it's pretty tricky to make sure that redundancy is achieved. But the cost of doing that is not very high. So in a traditional scenario, there might be 2 servers and 1 load balancer in front of them. And you have what is called as a standby. So one of those servers is serving 100% of traffic, but if load balancer figures out that the server is down, it diverts traffic to the other server. Now this is kind of wasteful because every server needs to be able to handle 100% of the load. So we're over provisioning for 200% of the load expectation, and as a matter of fact, we do 100% over provisioning. The other way of handling this situation is to have a load balancer that serves a kind of round-robin scheme. It serves 50% of load it diverts 50% of load to each of the backend servers. But again, it doesn't exactly solve the problem because we're still provisioning for 200% of load expected. Still, every server needs to be able to handle 100% of the load. So we're still doing 100% over provisioning. But in this scenario, if we have 3 servers behind the load balancer, each of them is taking 33% of the load. And if one of them fails, we only need to over-provision 150% because the other 2 servers will be able to handle 50% of the load. And obviously we don't have 3 servers, we have multiple servers. So we are able to, using load balancing, we are able to achieve redundancy, usually n+2, which means that we have 2 standbys, pretty cheaply and pretty efficiently. Now, the opposite of failure sometimes is too much success, which means too many users are using our services. And obviously, more users usually is better, but too much of a good thing can be a problem because we might not be always prepared to have a certain user base of a particular service. So we can do several things. First of all, if we were not Google, we could borrow our machines from somewhere. For example, Amazon EC2 does rent machines. But in all fairness, if we went to Amazon and told them how many servers we need, they would just say, no way. So as a matter of fact, we as Google need to handle things like that on our own. What we can do is plan for launch spikes. So when we launch a new product, we would over-allocate resources. So if we think that there will be 1,000 users on the first day or 1,000,000 users on the first day, we would over-provision by 10 times. So we would plan for 10 million users. And sometimes we would get 1,000 users because people don't like the product. Well, fair enough, but we need to be prepared. The other way of doing things in this case is to turn off non-essential functionality and repurpose machines that supported it. So for example, if we see a lot of machines failing and our data centers are going down, we still want to serve the users which are searching on google.com. But what we would do in this case is we would serve from a smaller index of websites. So you'd still get your results, but they would not be coming from the biggest index. So serving that request would be cheaper, so we can be still serving while we're experiencing big trouble. Another way of doing it would be to limit signups, and sometimes in cases of new products we do that. It's also great for marketing. It makes people want those products more. But you know, Google is not a startup anymore, and we feel that people have the right to use our products. So limiting signups is usually not something that we would want to do after an early stage. The other thing to consider is machine management. So obviously, to run 1,000 processes, you need 1,000 machines, and you need to call those machines somehow and address those machines somehow. There are not enough Smurfs or Star Trek or Star Wars characters to name those machines after. And even if we did have 1,000 Star Wars characters, it would be kind of difficult to remember which service runs on Smurfette or Han Solo or whatever. So we have a scheme of calling those machines. But once you have a scheme, you kind of need a database to tell which service runs on which machines, and possibly make sure that a service X runs on that machine. If that machine goes down and then goes up again, restart that service on that machine. So machine management is a big one, and I think Google has solved it exceptionally well. Another thing is change management. Obviously, downtime is not an option, and Google services are supposed to always be up. But just to give you an anecdote, whenever Gmail goes down, it doesn't happen often, but the next thing we get is a call from Twitter, and the Twitter guys say, you know what, I think your Gmail is failing because our Twitter is failing as well. So many people seek for Gmail is down on Twitter that we can't handle this. Yeah, I do that myself. But there's no scheduled maintenance for most services. I think most people would be quite upset if you try to access your email and it would say, you know, it's down for maintenance until tomorrow. So essentially you have to make all changes in flight, or take a fraction of service down. But if we take one data center down to upgrade Gmail to a new version, it means that we lose some redundancy. So that means that we need to have more redundancy to start with, to ensure that we have redundancy when we're making changes, right? We also need to think about compatibility, because when we have multiple servers and multiple services talking to each other, and versions of those services might change, we need to make sure that the version 1 of one service talks to version 2 of the other service and the other way around, and there's a compatibility behind it. So you need to make sure that the format of messages sent between different services is understood by everyone. Google has its own format. It's called protocol buffers, and if you don't know it, just check it out. It's very, very good, and it ensures that we can achieve that compatibility very easily. Another thing to consider is how to recover from a disaster. So, for example, if your major data center burns down, or if a software bug silently corrupts data over months and nobody notices it, and now suddenly all of your email is corrupted. Well, saying, oops, we didn't think of that, will not bring us any good PR. So we need to prepare for emergency scenarios. My own team is a part of emergency scenario where we back data up to tape, and we replay those tapes if things go really, really bad. But you need to know how to bring your service somewhere else if your data center fails down, so there are failover scenarios. And in fact, every year we practice a disaster recovery scenario. So there would be a scenario, for example, that there was a zombie invasion in North America. The whole North America is down. We need to run Google throughout North America. And make sure that teams are prepared to do that. The last thing is the business continuity. How do you know what to do when the thing that was being run by another person goes down. And obviously some people know a lot about the service and they leave. They move to other teams, or they move to Facebook, or they move to, be farmers. And new people come. And everyone needs to do their share of emergency response. Everyone needs to know what to do if things get really hairy. And as a matter of fact, one of those exercises that you do during your trainings is to troubleshoot a service that you've never heard of. So someone just calls you and says, look, that team got stuck at the airport, they have no internet, and something really broke down. You need to make sure that it's up again. And you see the service and you go like, I've never seen that before, what do I do? So obviously there is some documentation going on, but as a matter of fact, those services are very similar. There is a Google way of doing things in engineering, and my service is probably very similar to another guy's service. So it makes things much, much easier. So to conclude my tech talk, I want to say three things. First of all, having a great product is one part of the solution, and our software engineers are working hard on making sure that products are really nice. But getting those products to scale requires a lot of very specialized work, which is only tangentially related to the product, which means that running services is very similar, but it's very different than writing those services. So in fact, I would be more competent to run Gmail as a service than someone who wrote Gmail, because running services is a very, very different job than writing them, and so is scaling. With that, I thank you for your attention, and I invite you to ask any Google engineering related questions.
Thank you, Marcin. It was a pleasure to listen to you. Question.
Thank you, Mr. Marcin, for your presentation. I want to ask you about the reliability of deployment of third-party cloud-based applications. And I think my friend has a question.
Mr. Marcin, I would like first of all to thank you for coming to Tunisia, and I would like to thank you for your talk. I liked your presentation very much, but my question wouldn't be so much related to the presentation. Well, Mr. Wissem told us previously that you have done some community work, and that's what made Google recruit you. Can you please tell us more about it? Thank you.
Sure. Let me start by answering the first question, which was what do I think about reliability of